4.2, we're going to take a look today at prime and composite numbers. I've probably already used these words when we were talking in section 4.1, and you probably have a pretty good idea of what they mean as well. But we're going to start with definitions that are precise so that we make sure that we are actually doing and talking about the same thing. Let's do our leading idea first. Prime and composite numbers reveal an elegant structure in the natural order, reflecting a purposeful and intricate design. The uniqueness of primes and how composites build from them points to a creator who values individuality and interconnectedness. Integrating faith with these concepts deepens appreciation for mass patterns and inspires teaching that honors the balance of complexity and simplicity in creation. Let's pray. Dear Heavenly Father, I thank you for an opportunity to be here today. I thank you that we're in out of the rain, and I thank you for these students being here. I pray that you would be in our class session today, help us to make sense of what we're working with and to be able to be accomplished. We pray in Jesus' name, amen. Primes. A prime is any positive integer with exactly two distinct, that's an important word, distinct positive divisors. Distinct means different. So, for example, the number 2 is prime because 2 cannot break down into anything except 2 and 1. And 2 and 1 are two distinct numbers. So give me another one. It's prime. 7. 7 breaks down into 7 and 1, right? It has only 2 factors, itself and 1, and they are distinct. Notice what this means. The number 1 is not prime. How would 1 break down if I did the same sort of thing I've been doing on the others? 1 and 1. That's 2 factors. Why does it fail? They're not distinct. Okay? So 1 is not a prime number. That's important to know. It does come up periodically that people want to make it 1. Sort of by its nature, it fits sort of half the description, right? It is not a prime number. A composite number is any positive integer with more than 2 distinct positive divisors. So, for example, we'll go with the number 6. 6 has as its divisors 1 and 6. But what else does it have? 2 and 3. It has more than 2 divisors, so it's composite. Is 1 composite?
With more than 2 distinct. Not more than 2, they're not distinct.
So it says more than 2 distinct. It has the word distinct in there still. Is 1 composite? We said 1's not prime. 1 is also not composite, right? It does not have more than 2 distinct factors. It still just has 1. So this is one of those places in mathematics where we're not dividing them into 2 separate categories. There's a third category, and it includes the number 1. Or you can say 1 doesn't fit nicely into either of these descriptions. It's not categorized in this way. Okay? So it kind of feels like the discussions we have with our children sometimes as to whether or not God is male or female. No, he's not. Because he's not human, and that's a human characteristic that he created, right? He is something else, something other than. And 1, in this case, is something other than. It is not prime. It is not composite. Factorization is any expression of a number in factored form. Any expression. So when we talk about factorization of, let's say we have the number 12. One factorization of the number 12 would be 2 times 6. Another factorization of the number 12 would be 3 times 4. Both of those are considered factorizations. So a factorization is not a unique thing. And we could even go so far as to say that 12 is 12 times 1. So in the case of composite numbers anyway, this factorization process is not a unique process. However, prime factorization is. So prime factorization is a factorization containing only prime numbers. So if you take a look at my example above with the number 12, none of those are prime factorizations of 12. Because in every case, at least one, if not both, it's at least one, all of these actually, exactly one, have a composite number in them. So if you look at 2 and 6, which one's composite? 6, right? So it's not two prime numbers. If I look at 3 and 4, which one's composite? 4, not two prime numbers. And if I look at 12 and 1, 12's composite, right? So none of those are actually prime factorizations of the number 12. If we were to want to do a prime factorization of the number 12, let me show you what it is, but then we'll talk about how we go about finding them in a moment. The prime factorization for the number 12 is actually 2 times 2 times 3. It takes more than just two numbers. That's okay, it can do that. But the prime factorization is unique. If I were to do the prime factorization for 12 and anybody else in the universe does the prime factorization for 12, our answers will be exactly the same. There's no variability here, okay? A lot of times in math, there's actually variability in things. You might always not think that, but that happens a lot. Think about some of our problem solving ways, like how do we do things and stuff like this, right? There's more than one way to do stuff. Well, there's not here. There's only one answer that comes about when we look at prime factorization. So what we're going to do next is we're going to look at a couple of different ways of doing prime factorization. And we're also going to look at what types of numbers sort of move us into maybe a different strategy. So we're dealing with just a large number. This is 23,660. I'm going to show you two ways to do prime factorization for this. But the answers will be the same, right? Because prime factorization is unique. So 23,660, one way of doing it, and probably the one that you're most familiar with, is called a factor tree. So you look at this number and you find whatever you can as a factor for it, okay? Now this one ends very nicely in 0. So I'm inclined, seeing that it ends in 0, to divide it by 10 and to get 2366. Because I know that it divides by 10 because it ends in 0. Now, whatever the ending of these branches are, if they're still composite, they still continue to be factored. So 10 is still composite. What will it factor into?
5 and 2.
Yep, 5 and 2 or 2 and 5 either way. Now, at the point when you see 2366, you might now at this point say, I don't know what it divides by, as sort of like a bigger number. But you do know something it divides by, guaranteed. What does it divide by? Guaranteed divides by 2. How do you know? Ends and even. Okay, that's just why we did all those divisibility properties in the last section. Definitely divides by 2. So if we divide 2366 by 2, and you're welcome to grab your calculator for doing that. We're not in chapter 3 anymore where we were doing the division all by hand. It's okay. What is 2366 divided by 2? Excellent, 1,183. At this point, I'd like for you to notice that there are some primes at the end of these branches now, right? Do you see them? There's 3 of them. So as a hope that we're not going to lose them later, I'm going to circle them right now in a different color. You can circle them in the same color, but I don't want to lose those prime factors. Those are part of my answer. So I'm going to stop the branches extending down from them because they're primes, but they are part of the answer. 1183. 1183 is not prime. It does divide by something, but we don't get sort of the freebie that it's even anymore. So what might we try if we were looking at 1183 sort of in a structured way? What might we try next? Start with 2. I would do 3. I would just go up. Okay, so I would start with the smallest prime I know, 2. I would say 2 doesn't work. Let's see if 3 does. I know you can divide this by 3 in your calculator, but you could also check it really quick to see, right? 1 plus 1 plus 8 plus 3. What does that give me? 13. Does 13 divide by 3? No, so this won't either. So the next prime's 5, right? We skip over 4 because it's composite 5. Will 5 divide this? No, because it doesn't end in 5 or 0. So the next prime after 5 would be 7. We don't have a property for 7. So if we try to divide this by 7, what do we get? 7 and 169? Yep. And 7 is the prime, or is a prime from that one. You might, at this point, recognize 169. It just kind of depends on what math you've been introduced to or focused on before now. 169 is a number that sort of comes up. It's actually a perfect square. If you don't know that it works, right, it's 13 and 13, just so you know. But if you didn't know that, we would just keep working our way up. We would try the 169 and try again dividing by 7, and it's not going to work. And then we do the next prime. So we can't do any evens because they're all divisible by 2. So 8 is not a prime. 9 is not a prime because it's divisible by 3. 10 is not a prime. We would try 11. 11 wouldn't work. 12 is not a prime, so we have to try it. We try 13, and 13 would work. So you just keep stepping up on your prime numbers for doing the division. So even if you didn't recognize this at that point, now you can get that this is a 13 and 13. So we end up having these pieces that are all circled as our prime factors. And the way that we write our prime factorization is we start with the smallest one first. That's a 2. And how many of them are there? There's 2. So we're going to write that as 2 squared. And put a dot between them. The next one's a 5. How many of them are there? Just 1, so I just write 5. The next one's a 7. How many of them are there? 1, so I just write a 7. And the next one's a 13. How many are there? 2. This is the prime factorization of 23,660. How could I check it?
Multiply it out.
Could multiply it out. That would at least tell me that it gets me back to the right number, right? That it is a factorization. And then I know that it's a prime factorization because all of these bases, 2, 5, 7, 13, are prime numbers. Okay, all good? Okay, have we seen factor trees before? These are the ones that I've typically seen in curriculum that you guys have seen, okay? There is a there is a more structured way of doing this. One of the pitfalls of this, by the way, is that students' work is not usually as neat as mine is on the screen. And so they lose a factor somewhere. They weren't carefully keeping track of them as they got to the end of the factor pieces. And so they just simply miss something at the bottom. If they check it, like we mentioned in multiplying back out, they'll realize they missed something. But if they don't check it and they're just moving through their work, that's unfortunate. So there is another structured way to do this. And we're going to do the 23,660 still in this one. And we're going to divide, it's going to look like an upside down division, okay? You could do it from the right side up division, it's fine, but I kind of like going down because you go down a page a little bit more naturally. When you do this, you need to start with the smallest prime number that divides this, which means we start at 2. I don't care that it divides by 10, that's going to work itself out later. We start with 2 because 2 will divide this. So if I take 23,660 and divide by 2, what do we get? I have written down 11,830. Does that sound right? Okay, great. So I will do 2 again because it's still even. So we'll try it again. So I do 11,830 now, divide by 2.
5,950.
50 what? 5?
5,950.
15. I heard that wrong. Sorry about that. Okay. Will it divide by 2? No. So then we go to the next prime number, 3. We'll add these digits together, 5915. What happens if I add those together? You get 20, right? And that doesn't work. So 3 is not good. So we've done 2. It's not going to work. We've done 3. The next prime number is 5. Is it divide by 5?
Yeah.
Yeah. So we'll divide by 5. So what is 5915 divided by 5?
1,180.
Okay. We don't need to test 2s and 3s anymore. We already tested them. They didn't work before. They're not going to sort of somehow work now. Like, we're done with those. So we keep moving our way up the prime numbers. Does this divide by 5? Because that's what I just divided by. No. So the next prime number would be 7. 1183. We know it divides by 7 because we saw it just a minute ago. It gave us 169. We'd do the same thing again. We'd say 169, try divide by 7. It won't work. The next prime's 11. It doesn't work. The next prime's 13. It does. Like this. Okay, so benefits. All your answers are in one row, like this, right? that's kind of friendly. Not only that, but they're in order, smallest to largest, and all the ones that are matching are paired together. So I can very easily see that there's 2 2s, 1 5, 1 7, and 2 13s because I can just read it from top to bottom. Negatives, this is very structured in the sense that you don't have any flexibility. You have to divide. Like if you're doing it in the strategy, really, you're supposed to be dividing by the smallest prime that works. So if you noticed that it divided by 10, you don't get to divide by 10 on the outside. You start with 0, you start with 2, right? And then you go to 3, and then you go to 4. So it's got this sort of sense of structure that's really nice on the ending, but it might not be very friendly for a student who just doesn't see it that way on the beginning part of it. So pros and cons. All right, so some of our numbers start out looking like this. They're all multiplied out. We're going to break them down, and it looks like this. You can pick which strategy you like. Doesn't matter to me in the slightest. This is not one of those things where I'm going to be like, on your test, like show me another way to do it. Like I've done that sometimes. But these are the same thing. This is really not different. It's just structuring, like ordering it different. That's not really a different thing. So sometimes though, your values are already partially factored. Okay? This is partially factored. Well, I shouldn't even say that. It is factored. It's just not prime factored. So it is partially done because I've got it in some pieces of factors. You do not want to multiply this all back out and start all over. That would be a waste of your time, guaranteed. You want to take where it is and continue breaking it down from where it is. So the bases themselves here, unfortunately, are not primes, and that's what it takes to be prime factored, right? 16 is not a prime, 81 is not a prime, and 6 is not a prime. Like literally none of them are primes. So we're going to take each one of those individually and break them down. So we'll do 16, 81, and 6. And I'll do factor trees for them just because they're small, and that'll be just fine this time. So if I do a factor tree for 16, I'd get 4 and 4. The 4s will all give me 2s. So this gives me 4 2s. So, okay. All right, let's do this for 81. 81 factored, 9 and 9. 9s break down into 3s. So I have 3 to the 4th. And then I've got 6. 6 is 2 and 3. So I just have 2 times 3. Now I'm not done, but I do have the bases individually in factored form now. So what I'm going to do next is I'm going to take each of those bases and I'm going to replace the 16. I'm going to replace the 81 and I'm going to replace the 6. So I have 2 to the 4th replacing the 16 and it has a 4 on the outside. I have 3 to the 4th replacing the 81. It happens to have a 4 on the outside. And I have a 2 times 3 with a 6 on the outside. Now back in section 3.4, we looked at properties of exponents. So we're going to apply them here. So I have 2 to the 4th to the 4th. What do I do with the 4s? Do you remember? You multiply them, right? This one's your multiplication. So we're going to multiply those together. So I have 2 to the 16, right? Now I have the same thing happening on my 3s. I have 4, 4. So I'm going to multiply those, 3 to the 16. What's the property for when I have 2 numbers multiplied raised to a power? They each get the power. You can distribute the power over multiplication, right? So this would then be 2 to the 6th and 3 to the 6th. Now, technically that's factored, but it's not simplified, right? Those are prime factors. It's all there, but I need to simplify because I have some matching bases. This 2 and this 2 match, and this 3 and this 3 match. So what do I do when I have, we'll do the 2s first, 2 to the 16th and 2 to the 6th. Yeah, that's when I add the exponents. So this is 2 to the, what's 16 plus 6? 22. And then I actually have the same thing for my 3s, right? 3 to the 22. There's nothing that says they would have had to have the same exponents. It's just the values they gave us and the way they gave it to us, okay? Everybody good? Okay, let's take a look at C. C looks partially factored as well, or at least kind of like the last one, but what's different about it? There's addition, and that addition does change things. Yes, ma'am?
Sorry, I have a question about the last one. So you said that you can't do 2 times 3, where it's like 6 to the 26th?
So if we did 2 times 3, we would get 6, and you're right, but 6 would not be prime.
Oh, yeah.
Yeah. So would it be a condensed way of doing it? Sure, absolutely. Would it be a factorization? Yes, it just wouldn't be a prime factorization.
We did that a couple.
We did. We did that a couple chapters ago because we weren't looking at divisibility with prime and composite numbers. Yes, you're right. Okay, do you guys remember doing that?
Yeah.
Yeah, we had one like that. You're exactly right. Okay, this addition changes things. So what happens is that we actually need to look for what is factorable from the first piece, like this piece, and from the second piece. Another way of saying that is we can say, what do they have in common? So they both have a base of 2. Agreed? Okay. How many 2's do they have in common? Well, the first one has 2, and the second one has 4. So how many of them are common to both? 2. Okay? So this first 2 squared got completely pulled out, so I'm going to do a 1 in its place. The addition is still present. And the 2 to the 4th had a 2 squared pulled out, so how many 2's remain? 2. Okay, we're filling a lot of blanks, so hold tight. They both have a base of 3, right? How many 3's do they have in common? They have 4. There's 5 in the first one, there's 4 in the second one. So they have 4 3's in common. So how many 3's remain from the first value? This is what I'm calling first. This is what I'm calling second. There's a 3 still there, right? There's a 3 that remains. And if I have the 3 to the 4th and I completely remove it all out, it's like dividing, I have a 1 that's left. 3 to the 4th times 1. Okay? They have a base of 7, both of them. How many 7's do they have in common? 55, and identically 55 this time, right? So that 7 to the 55 got pulled completely out of each of them. Like that. Sorry, I missed that. Times 1 before. So each of these 3 pieces, 1, 3, 1, and then 2 squared, 1, 1, are coming from divisibility. I've divided the piece that I've pulled out of what was there, and I'm writing down what remains. And when I divide something by itself, I get 1. So the part on the outside is done. 2 squared times 3 to the 4th times 7 to the 55th. But what's inside actually has the ability to be combined and simplified. What is 1 times 3 times 1? 3. And what is 2 squared times 1 times 1? 4. Okay, we're going to rewrite the 2 squared, 3 to the 4th, 7 to the 55 in front. What's 3 plus 4? 7. Now, sometimes when this happens, you get some number that didn't exist already before. Like maybe I got a 13 here. That's possible, right? And I'd be done. But at this point, while it's prime factored, it's still not simplified because there's a 7 that I just got and a 7 to the 55 in front of it. So those can be combined. This is 2 squared, 3 to the 4th. How many 7's are there? 56. All right, I've already talked about this. I just didn't give you the title of it. It's called the Fundamental Theorem of Arithmetic. Sounds important? And it is. It's important. Anytime somebody puts fundamental theorem on it, it means it's fundamental, right? It's important. And it says the following: each composite number can be written as a product of primes in one and only one way, except for the order of the prime numbers. And that's what I was telling you happened on the number 12. Right? 12 is 2 times 2 times 3. And I could change the order around, like I could write 2 times 3 times 2 or 3 times 2 times 2. I could shift where the numbers are, but the prime factorization is unique. It's exactly the same. There's no other way to do it. And that's what this says. So as we take a look at this, we're going to see an example here in a minute, example number 3, that considers why this can be done. But first, let's look at theorem 414. 414 says that if D is a divisor of N, then N divided by D is a divisor of N. And aside from the fact that it looks funny because there's N's and D's in it, we've done this too. Okay? Back in section 1, we had 24 at one point. And it had a question that asked us to divide and tells all the divisors of 24. Okay? Nod your head if you remember that. Do you remember that? It was in the notes. And one of the things that I said is that it's easiest to make sure that you don't forget or skip any of the divisors if you do them how? Do you remember? Like if I know that 2 divides 24, what do I automatically also know divides 24? 12. So I did them in pairs. That's all this theorem says, is that divisors occur in pairs. If 2 divides 12, then 24 divided by 2, which is 12, will divide 12. Divisors occur in pairs. Now, sometimes the pair could be its own, right? So like if you did 36, 6 times 6 is 36, so he's his own partner. That's fine. But it's still a pair. It's still 2 numbers that kind of go together. So that's what this theorem is telling us, is that divisors occur in pairs. Okay, the next one's actually super helpful. The next one tells you that if you have a composite number, right, and you're trying to figure out, or if you're trying to figure out if a number is composite, that there's sort of an upper limit on what you have to test. So if I had given you a number that was like 32,477, you don't get the automatic freebie of it ending in an even to know that it works, right? But if you start dividing by all these primes, when do you get to stop? Like if something doesn't actually work, when do you get a stop? Because I don't want to go all the way up to 32,000 something, right? Like that seems like unnecessary. There's got to be a place that stops. Well, this is actually telling you that if you have a composite number, then it will then n has if n is a composite number and p is the prime factor, then p squared will be less than n. Okay? So in particular, 416 is how it works. If n's a whole number greater than 1, and it's not divisible by any prime number p, where p squared is less than or equal to n, then p is prime. So let me give you the example that I just gave you. We'll see if I can remember what it was, 32,000 something. We'll go 177. I don't want to go up to 32,000 dividing this sucker, right? I mean, I hope that it divides by something and works out to be composite really fast. Because if this is just one really, really big prime, it's going to take me forever to get to the decision that that's what it is. Well, what this theorem actually says I can do is that I can take the square root of the 32,177. So somebody tell me it'll probably be a decimal. I don't think this is a perfect square. So somebody tell me in decimal form, give me like 2 decimals, what does this give you if you take the square root? Okay, that's good, yeah. So this is telling me I don't have to test numbers all the way up to 32,000 something. The highest I would have to go, and admittedly it's still large, but the highest I would have to go is 179. I don't need to go any higher than 179. And while 179 is certainly still large, it's way less than 32,000. So this puts an upper limit on our testing needs when we're working with composite numbers. So let's take a look at an example that's smaller, 967, much more manageable. What this says is that it wants us to find the biggest number we would need to test. Okay, we wouldn't start there. We'd start with small numbers and work our way up, but we kind of want to know when do I get to stop testing? So I take the square root of 967, just like I did my square root of my 32,000 number a minute ago. What is the square root of 967? And I should put approximately, because seldom does that work out to being a whole number. If it does, that's great. You know you're automatically composite and those your values were done. But what is this approximately? And again, 1 or 2 decimals is enough. 31.1. Fabulous. Okay, so the largest prime number that is smaller than 31 is what? Or 31.1 is what? 31. So 31 is prime, okay? So if this had said 30, like 30.1, we wouldn't put 30 because 30 is not prime. We'd go down one, we'd say 29. This is the largest prime number that we would need to test. that's pretty small. I mean, we wouldn't have to test all that many numbers if I can have an upper limit of 31. So I harped a little bit on the fact that 1 is not prime at the beginning. This actually shows why it matters. It says show that if 1 were prime, if we decided it gets to be included, then a number would have more than one prime factorization. So we're going to do something real quick and simple. I'm going to do the number 15. All right, 15. What is a prime factorization for 15? 3 times 5. According to the fundamental principle of arithmetic that we just did a few slides ago, this is unique, right? There's no other prime factorization. Agreed? And that's what that told us. If 1 were prime, then this would also be a prime factorization, right? But not only would that, so would this. And so would this. And so would this. If 1 were prime, the fundamental principle or fundamental theorem of arithmetic would be false. True? But do those 1s do anything for me? Absolutely nothing. They don't help to clarify the situation. They don't give me further divisibility information. They're not productive. Okay? So the reason we're not using the 1s is there's several reasons. One is those things I just said. But the biggest problem is that it would make the prime factorizations not unique, right? So my prime factorization and Emma's prime factorization could both be right, and they could be different. That's not what's going on. We want unique prime factorizations. All right, let's look at Mr. Arbor. Mr. Arbor wants to plant apple trees in a rectangular array. Okay, so we know what arrays are. We did that, right? That was section 3-4 as well. We've got arrays like multiplication. He's got 36 saplings, these little trees. He wants to find all possible numbers of rows if each row is to have the same number of trees. Okay, so imagine it's like rows, on the cupcake pan. It's rows in the classroom. They're supposed to all be the same number of desks and, deep and wide kind of deal, okay? So as we're taking a look then at 36, what is an option of the number of rows that he could do? 6. Okay, so if he did 6, he'd have 6 rows with 6 trees in each row, right? So the 6 and the 6 occur in a pair, just like we talked about before. What's another one? 2 and I think it's 18. Is that right? 2 and 18? 2 and 18. And we're not doing this in a very orderly way, but the numbers are small enough, we're probably going to be okay. All right, we've got 2 and 18, so we have 2 rows. We have 18 rows, depending on your perspective. So 2 rows of 18 or 18 rows of 2. What else could we have? 3 and 12. We've got 3 and 12. So 3 rows of 12 or 12 rows of 3. There's one more we could have. Oh, there's more than that, sorry. 1 and, what was it? 1 and 36, that was one I was thinking of, but I missed one. 9 and 4, and I missed it because we weren't going kind of in order, which is fine. 9 and 4. My suggestion is to start with the 1 and 36, and then go to the 2 and up from there to not miss anything. But as long as you get them, it's okay. We can have rows of any of those lengths. So we can have a row of a 1, 2, 3, 4, 6. Those are the small ones if you think about it that way, but you can also go then to 18, 12, if I'm going in order. 12, 9, I missed 9, 9, 12, 18, and then the 36 itself. So these are all possible rows that we could have. Okay, I'm going to do the last problem. I'm not going to make you do homework over the weekend though, okay? So we get just a plus and a minus, so hold tight for me for just a second. Bob says that to check whether a number is prime, he uses the divisibility rules he knows for 2, 3, 4, 5, 6, 8, 10. He says if a number is not divisible by these numbers, then it's prime. How do you respond? Okay, will it work? Let's start with that. If he tests 2, 3, 4, 5, 6, 8, and 10, will he for sure know if a number is prime or composite?
No.
Nope. Can you give me an example, Kira?
He could multiply by 7. And that's prime, but it could be.
How about I use 49? Will that work for you?
Well, 7 and 7 are both prime.
Yep. So if I used, well, let's see if my number is 7 and I use the divisibility of all these things, I will find that 7's prime, which is exactly what he's saying I should be able to do. 49. Does 49 divide by any of the numbers that Bob's going to test him? No, it does not divide by any of those numbers, true? So he would tell you by his rule then that 49 is prime. Is 49 prime? No, 49 is not prime. Because 7 times 7 is 49. So interestingly enough, not only is he going to be wrong in the sense that he's going to miss some this way, he's also going to have tested things that are unnecessary to test. He doesn't need to test 4, he doesn't need to test 6, he doesn't need to test 8, and he doesn't need to test 10, because those aren't prime numbers to begin with. If he's already tested the number 2, he's covered all those even numbers. He doesn't need to test them. So in some ways, he's not testing enough things, and in some ways, he's testing things he doesn't need to test in addition. Okay? So are those divisibility rules helpful? Of course they are, but they don't tell us about prime divisibility specifically. Okay, so what we're going to do is we're going to table this. You don't have to do the group work and homework. We'll do the group work next time. If you want to start it, you absolutely can. I can tell Allie's really excited she wants to start. So you can totally start the homework over the weekend. Don't do the group work, though. We'll do the group work in class, and we'll move on to 4-3 in class next time as well. Okay? All right.